Hello everyone, I think it's about 1:30 Pacific time. Probably time to start the webinar here. Thank you for joining us. This webinar will be on electro-optic modulation solutions and polarizing fibers for cold atom and quantum applications. My name is Yves Dice. I am the North American sales manager for iXblue Photonics. I will be presenting today with Henri Koch, who is our Vice President, heading the Electro-optic Modulation Division of iXblue, and Hervé Gouraud, who is our Sales Director, will also conclude the presentation. I'll start with a quick outline of the talk. I will start by providing an overview of iXblue and its photonics division, and then go to the market that we have identified in the space of quantum optics. We know lasers play an important role in quantum optics, and it turns out our components are well suited for improving and enabling applications in quantum optics. In the second chapter, we will tell you more about electro-optic modulation solutions and the technical choices we've made that make us the leader in the market in terms of performance, especially in the near infrared. We will then move to describe an integrated solution of 780 nanometer source that was developed for internal cold atom accelerometers at our division joint venture with called iXblue. So once we cover the electro-optic modulation solutions, we move to other components such as polarizing fiber, which is an easy way to polarize the lasers. We'll also touch on the narrow bandwidth filters and laser sources. So let's get started. Navigating the quantum world with iXblue. So who is iXblue? iXblue is a French company. It's actually a private company, headquartered in Paris, France. And we have about 700 employees. We're known for navigation solutions, in particular the fiber optic gyroscope. We have about 40 years of experience in optics, and we generate about $145 million in revenue over the years. So we have many locations around the globe. In the US, we have 2 locations, one in Denver and one in Boston. We offer quite a few products, starting with navigation solutions, hence the interest also in quantum measurements using optical solutions to increase the precision of those measurements. As you can see, we're quite diversified in the area of navigation. We provide acoustic sensors, we also build chips to are filled with our sensors, and surveying solutions. But what is of interest today is our photonics division, and I'll be focusing on that and the products we have there. So the photonics division is 2 entities. One entity provides modulation solutions. It's based in Besançon, which is close to Switzerland. So we make and design electro-optic modulators, but also the RF amplifiers that use to drive them, the bias controllers. And we also make integrated turnkey systems where we integrate our components with the laser and other components to provide reference sources. The other entity is based in Brittany, that's on the west part of France, and there we make specialty fibers and the photonic components. So mostly doped fibers, but also polarization maintaining fibers and polarizing fibers, we'll get to that, and fiber black grading. So now the quantum world. Our components actually have found ways to go into that domain, and we've identified 3 main areas of interest in quantum. The first one is quantum computing, where electro-optic modulators can be used as switches for switching lattice polarization by 9 degrees, for example. There seems to be a renewed interest in that field also for optical pulse generation. This is the case also in quantum communication, where we have interest for quantum key distribution type of applications, short pulse generation. And finally, the quantum measurements, which typically include atomic clocks, gravimeters and accelerometers, magnetic field measurements, imaging, where people are looking for solutions for cold atoms. And that's one of the focus also of the talk here. So as you all know, in the quantum world, lasers are a very important part. The wavelength is typically related to the atomic transition that is used. Important parameters are the laser power, but also laser stability and line width, the tunability of the laser, the agility of the laser. And that's where our products actually can help, because the electro-optic modulators can provide solutions to increase the stability of the laser, to increase the tunability or to provide tunability to your laser, and increase the agility of the laser, so the spinning speed of your laser. So that's where we find applications in the quantum world. We've identified a few applications that require electro-optic modulators and filters. The first one is to stabilize a laser source using the Pondra-Hall technique, which is well known. A very stable laser is always welcome in this field, right? So we'll touch on that. We have solutions to generate multi-line lasers, either for carrier frequency and first or fourth order sidebands, for cooling and repumping lines during the magnetic trap, optical trapping. There you can use either phase modulators or amplitude modulators with a filter. Typically, people use phase modulators. If you want more lines, you can also do frequency counts using phase modulators, so a very broad spectrum, multiple lines. On the other hand, you can also generate just one single line, so you can do that either with a Mach-Zehnder interpolator that filters, or we'll also go to the carrier suppressed single sideband option using what is called an IQ modulator. Finally, we have solutions to generate very short pulses that can be customized, and we'll give you a few examples on that as well. Now, moving to the electro-optic modulation solutions for the quantum world, let's start with describing what we make, what is an electro-optical modulator, and what does it do. So we have a few pictures here. On the left, you can see the lithium niobate chip. So at iXblue, we actually control the whole manufacturing process up to the finished packaged product, which you can see on the right-hand side. The electro-optic modulator are based on a waveguide that's written on a lithium niobate substrate. We deposit traveling wave electrons, and the electrical field will basically change the material refractive index, and therefore change the speed of propagation of the light and shift the phase of that light. So that's how you can obtain several different results in phase and in frequency. The first option is the phase modulator, where you can slow down the light or speed it up, resulting in sound generation, for instance, or carrier suppressed dual sideband. The next item is an amplitude modulator, which is actually a Mach-Zehnder interpolator. In this case, we use it to generate 700-second pulses. And in the spectral domain, you can see you can do carrier suppressed dual sideband generation. The last item we will go over is the IQ modulator. And this one is used to change the amplitude and the phase of a signal. And in particular, it's used for carrier suppressed single sideband generation. Now, we have made at iXblue a few technical choices that provide high stability and high power handling, especially in the mid-infrared. So in the quantum world, typically people are looking for solutions in the near-infrared or even visible. Unfortunately, lithium niobate is susceptible to photoreflective effects at lower wavelengths. So this prevents us from providing solutions in the visible and for wavelengths shorter than 760 nanometers. Now, that being said, we've acquired a unique and extensive know-how to make very good optical electro-optic modulators in the near-infrared from 760 to 1150 nanometers. And in the next slide, I'll go over the details of what technology choices we have made and how we became a leader in that field. The first important parameter is the process of how we manufacture the modulators. The most common way of manufacturing a lithium-ion modulator and writing the waveguide into the substrate is what's called the titanium in diffuse process. So this works well at 1550. Probably 90% of the modulators in the world are made using that process. But once you use the light at 780 nanometers, you can see on the right in the graph, you will have fluctuations in extinction ratio and fluctuations in insertion loss. And this is due to the photorefractive effect that is happening inside of the waveguide. So we actually use the anneal photon exchange technique to make the waveguide for near-infrared modulators. It's a bit more complex to implement, but it clearly provides an advantage in stability. If you look at that same graph, using a light at 780 nanometers, you have stability of the extinction ratio, and you have stability of the insertion loss. So today, we guarantee stable operation at 780 with the 20 milliwatts, and at 850 with 60 milliwatts, which are pretty good values for waveguide-based electro-optic modulators. In the next slide, we show improvements by using a different lithium niobate substrate that we specifically designed to increase the power handling of our modulators. So here we combine that with the process, and we show a graph where we have stable operation at 300 milliwatts of power at 1064 nanometer in this case, at basically room temperature. So that's another factor that increases our power handling and stability of the product. The final improvements that we made is using an X-cut versus a Z-cut. So in the X-cut, the electric field is around the X-axis of the lithium niobate crystal. It is a little bit less efficient than having a Z-cut, and you take a little hit on insertion loss, but the main advantage is that you don't have pyroelectric effect. For the Z-cut, because of the way the electrodes are mounted on the crystal, you have an accumulation of electric charges on both ends of the electrode, and this will create instability over time, especially over temperature. So we believe that the benefit of the X-cut configuration, which we call the X factor, is outweighing the slight hit on performance, and so most of the modulators we propose come with an X-cut. Now let's move to relevant solution, electro-optic modulation solutions for the quantum optic applications. The first application that we want to talk about is the Pondra Hall application, which is used to stabilize wavelengths of a laser using an absolute reference, such as a gas cell. So the way this works, and I'm sure everybody's familiar with it, is that you apply a small phase modulation to the laser source. And this obviously can be done using an external phase modulator. So that frequency modulation then is converted in amplitude as it hits the epsilon, as it's filtered by the epsilon. And you can use that as a feedback loop to lock the laser to the desired wavelength. Now, something that we have identified and that is an undesirable effect of the phase modulation is residual amplitude modulation at the output. And this occurs because you have a waveguide that is generated by the electrical field, where some of the light is coupled into and recoupled at the output of the modulator. So there's a paper that was written on that, and we can send you additional information on that factor, but it will eventually add an error to your feedback loop. And as a result, the stability will be not as good as it could be. So one way to improve that is actually to apply a DC voltage to the modulator. And this will basically vanish that induced waveguide and improve the RAM by about 10 dB. So we can send you some information on that. Here in this slide, we show the measurement that we took on the graph on the bottom. So we measure the residual amplitude modulation in dB versus the DC voltage applied, so from -20 to +20 volts. And you can see that there's some ringing happening, but ultimately you can find a sweet spot that is 10 dB better than what you would get if you wouldn't correct for that problem. So we offer solutions there over a wide range of wavelengths, from 780 to even 2 micron, actually. We offer low residual amplitude modulators, we can say that, and that DC coupled and typically come with a high impedance input. A slide that I want to add in this is this slide showing that we have delivered such modulator to NASA JPL for flying basically system in the Grace Polar mission. So it's basically 2 satellites, Tom and Jerry, that follow each other and measure the distance. And our phase modulator is used for the PDH technique in that system. And it's been flying since 2018 with good results. So we have quite extensive experience with space-grade type of systems with our phase modulators. This was a 1064. It can be done at all wavelengths, and I thought it was worthwhile mentioning. Staying with phase modulators, we can go to wider bandwidth. Obviously, so here we show the 5 and 10 gigahertz version that we have, operating wavelength from 760 to 1560 nanometers. You have to select which wavelengths you want to operate at, obviously, it's a different modulator. But each of them will feature low insertion loss and very good optical power handling, especially in the near infrared. We also have an option to increase the RF power handling coming in. So if you want to generate several sidebands for comm generation, for instance, you can do that up to 2 watts. In the graph that we show here, you can see in brown is the V5 versus frequency of our 5 gigahertz modulator, and it's sufficient for operating at 6.83 gigahertz, which is typically the line for rubidium. You would have a slightly better V5 of 3.5 volts. As you can see, even for the 9.2 gigahertz, you can use our 5 gigahertz version. This illustrates the comm generation. We have an application note on that as well that kind of gives you a good way to calculate the power in each of the sidebands. It basically follows a Bessel function that you input a sinusoidal input. So we can share some more information on that with you. But again, with those phase modulators, you can generate either multi-lines or comms as you wish, depending on the RF power that you input and the modulation index that you choose. Now moving to intensity modulators. We offer also wide bandwidth solutions in the near infrared, mostly for pulse applications in this case. So electro-optic bandwidth is about 40 gigahertz there, with a low electro-optic drift, which is very important because you want to have high stability and good repeatability of your pulses with a high extinction ratio of 30 dB. So below we show the S21 curve, which is relatively flat, up to 40 gigahertz, and the S11 curve in orange. We also make those same modulators at 1550. Some people choose to start with, let's say, 1560 nanometers and then double to 780 nanometers. The reason is mostly because fiber amplifiers can increase the power at 1560 and then you have more power at 780 as a result. So in that case, we offer a contrast of 40 dB with also very low DC drift and low insertion loss. And you can see the transfer function of such a modulator on that slide. Finally, we talked a little bit about the integrated solution. So here's an example of what we can do. typically for pulse generation, either single photon or quantum key distribution, we can generate as short as 30 picosecond pulses at 850 nanometers. Contrast is typically 30 dB, but we've done systems that provide up to 100 dB of contrast with square pulses or arbitrary waveforms. So if you're looking for a unique shape for your pulse with a low time zero, you can give us a call and maybe we can help you. Finally, moving to a bit more of a complex component. This is what we call the IQ modulator that was designed for carrier suppressed single sideband modulation. It was designed mostly for high extinction ratio. So it's two Mach Zehnders in parallel with a phase modulator. And with that, you can control both the intensity and the phase and generate a good carrier suppressed single sideband signal, as it is illustrated on the spectrum here. So we can guarantee 30 dB of extinction ratio for the carrier and 30 dB for the sideband in that case. Other variants of that can be full carrier single sideband, where people want to have also power still in the carrier, or residual carrier single sideband, where people want to match the power in the carrier and in the sideband. So those are all options that we can provide with that solution. Now we'll yield to Henri, who will go over the solution at the 780 nanometers that we developed for cold atom laser source used in our accelerometer.
Good afternoon, everyone. I will talk about the cold atom laser source that has been developed for several years in the frame of cold atom interferometry for different applications. Next slide.
Oh, sorry.
This laser source has been developed in the frame of a collaboration between iXblue and the laboratory LP²N in Bordeaux, which is specialized in atom interferometry. And the aim within this collaboration, iXblue tends to evaluate the feasibility of cold atom interferometry to go to inertial navigation systems and try to evaluate the feasibility of such a technology in the field of inertial navigation, that means gyroscope or interferometer. And after all this year of collaboration, we have been discussing in particular on the quality of the laser source that is involved in such interferometric atom interferometric application. So just to recall, the scheme show that the laser source in cold atom interferometry is used at several steps. The first steps is the cold atoms cooling in the first step with 6 laser beam orthogonal illumination of the gas. And then there is a 3 steps interferometer based on a Raman illumination with three pulsed laser beam that are applied to separate the atoms beams and to separate and then to recombine. And at the end, the laser is also used to measure by fluorescence the number of atoms in each states of the reaction. And so the one single source has to be used for all these steps. But in such a scheme, the laser source must be very agile because at least 2 wavelengths close to the fundamental transition of rubidium, let's say if we talk about rubidium, have to be modulated in phase, in amplitude, and also in frequency extremely rapidly. And the quality of the result at the end is very dependent on the On the parasitic interferometer, that means that the number of lines is of key importance, and the reduction of parasitic lines is really of key importance. So if we describe a little bit this mod box dedicated to rubidium called previous slide. Thank you. So we try to define a very agile and reconfigurable dual band emitter dedicated to this cold atom application, and able to generate all these different sequence of rubidium cold atoms operations. Switching times between each frequency sequence must be as short as 50 microseconds, and all this must be very agile, and this allowed thanks to the very flexible microwave pilot source. So this system has been patented, and is based on the use of telecom wavelengths at 1560 nanometer, and use the carrier suppressed single sideband modulation, and then second harmonic generation through a nonlinear optical device. And thanks to that, we are able to deliver two simultaneous optical lines close to 780 nanometer with a high rejection of the parasitic lines. And this rejection of parasitic lines is very important to improve the performance of the instrument, in particular regarding the atom interferometry metrology. Next slide. Thank you. So the figure on the right side of the image shows the instrument that has been designed in this frame, and that is used today currently in our laboratory in Bordeaux to characterize the cold atoms interferometry that we are working on, and in particular accelerometer. So our laser architecture combines an all-fiber IQ modulator operating at 1560, and then wavelength conversion thanks to a PPLN, periodically poled lithium niobate crystals that generate the 780 nanometer wavelengths to be applied on the rubidium gas to get the cooling atoms. And thanks to this carrier suppressed dual single sideband modulation scheme, and thanks to this IQ modulator, we are able to generate two optical sideband, very flexible, very agile, and that can be independently controlled in frequency, phase, and power with a control laser source. That means that there is no mechanical part or moving part. All this is controlled totally by electro-optic modulation. And so it's very flexible and very fast process. And we have been able, compared to standard phase modulators that have been used in previous configuration, to show a strong attenuation of the lines, of the parasitic line that generate parasitic Raman transition, and that reduce the performance of the, for instance, the accelerometer we are working on with this configuration. And today we are able to characterize down to 10 nano G our cold atom accelerometer. So on the left side is the whole scheme of our mod box, which includes a reference master laser, which is locked on a saturable absorption on rubidium. And this master laser is mixed with our slave modulator at 1560 nanometer, and then modulated by the IQ modulator. And we have inside the box an optical amplifier that generates the high power, an acoustic modulator to switch the optical power, and then the PPLN to generate the 760 nanometer. And the lines that are generated, we're going to see some performance, but can reach up to 500 milliwatts. Next slide. So on the right side is the image of the laser source mod box, which is applied on the reaction chamber, the vacuum chamber, which contains the rubidium atom that have been used for the acceleration interferometer, which is under development in our common laboratory. And this cold atom laser source is characterized by a dual independent sideband generation at 780 nanometer with a high agility on the tunability of the sidebands. We can control in a very flexible way the optical power of each band, and this separately, independently. We have high accuracy of the frequency tuning thanks to the microwave source, and with thanks to the IQ modulator, a very high rejection of the undesired parasitic sideband and harmonics. And thanks to the electro-optic modulation, it's a very fast switching. And if you remember, you should know that an interferometer with cold atoms sees some transition in the range of some nanoseconds, some milliseconds, a complete cycle being in the range of 10 Hertz for a total calculation. Next slide. So these are some of the feature of some specification of the resulting laser source. So the total output power, which is generated at the output behind the PPLN at 780 nanometer, is typically in the range of 27 dBm, that means around 500 milliwatts. So this is a total, but this power is split between the two lines that can be generated. So each line can be in the range of 20 dBm, means around 100 to 200 milliwatts. The line width, thanks to the very narrow master source that we use, is in the range of 20 kilohertz, so very high resolution. And we have a possibility of detuning in the range of 10 gigahertz, so it's very flexible. It allows to address any of the transition of the rubidium atoms, in the case of the rubidium. High extinction ratio, of course, it's about 25 dB. And the most important is the side parasitic line rejection around the harmonics of 6.8 gigahertz in the case of rubidium, which is the fundamental transition, and the parasitic line widths are below 20 dB and down to 25 dB. And this is very important for the quality of the interferometry that we can get at the output. Next slide. Okay.
Next slide. And back
Thank you, Yves.
Talking about the polarizing fibers we have and the fiber back ratings. So now that you have a source that you can use for some instances, well, you want to achieve a higher state of polarization, right? And it could be important for that atom experiment. So here we just illustrate the difference between a standard polarization maintaining fiber. You basically maintain the polarization on the two axes, the fast and the slow. With the polarizing fiber that we provide, we only maintain the state of linear polarization on one of the axes, typically the slow axis. And the fast axis, we vanish that polarization, or we basically make it vanish. And that's how it would work, because when you have a PM fiber, basically, and you have a PM signal, a linearly polarized signal that transmits, you would always have some light on both axes, fast and slow, right? And eventually, those two will beat like an interferometer, and you will have instability. So you can characterize that beating by what's called the depolarization length. After a certain length, you don't have interference anymore. And this is linked to the coherence length of the signal that you'll be sending in, which is the wavelength squared over the line width. And after a certain distance, in that case, both ion polarizations won't be interfering anymore. So typically, that the depolarization length is linked to the birefringence of the PM fiber, and it's about 2,000 times the decoherence length. So if you go to a concrete example of what we're talking about here, is that if you use a broad source, right, let's say 1550, you use a source that is a 15 nanometer wide. With the 5 to the 10 minus 4 birefringence index of a typical fiber, the depolarization length is 30 centimeters. So after 30 centimeters, we won't have that beating anymore. and there's instability of polarization. If you use a very narrow line width, which is mostly the case in for atom sources, as an example here at 780 nanometers with a line width of less than 2.5 gigahertz, your depolarization length becomes 240 kilometers. So that requires a 250 kilometer fiber before you can stop those interference from happening and have a stable output. That's what we say here. So if you use the PM fiber, you may have more power instability. The advantage of the polarizing fiber is that you will get rid of the second polarization on the fast axis, and therefore you won't have interference anymore. So this is the solution that we propose. So typically it's about 10 meters of fiber that coils. Here we give an example of a 70 millimeter coil diameter with 8 meter of length of fiber. And you insert that between your 780 nanometer laser source, for example, and your magneto-optical trap on the other hand. And that would provide you with a good polarization extinction ratio greater than 50 dB and improve the stability of the laser source. So the way it works is you have a graph here that shows the cutoff wavelength on the left here of a fiber. You will have a polarization maintaining area, and then you will have a polarizing bandwidth area. And you have to design each fiber for a given specific wavelength and a band of that polarizing. So in that polarizing bandwidth area, you will have the fast mode that's transmitting and the slow mode that is the slow mode that is transmitting and the fast mode that is going to release. So the fast mode is going to be absorbed. You can see in red the first curve here going down. As you increase the fiber length, you will increase your polarization because most of the light on the fast axis will be eliminated, while the light on the slow axis will get transmitted. This one is a bit redundant here. So here is kind of again the example of what we can do at 780 nanometers. We can provide polarization, polarizing bandwidth of about 50 nanometers, and you need about 8 meters of fiber. We can provide the fiber. We can also provide the polarizer, so we kind of coil for you, and we can guarantee a polarization extinction ratio at the output of up to 50 dB. So that could be of interest for your application. The other item that we have is fiber rack gratings. In the fiber rack gratings, we basically write gratings using UV lights, and we use two different methods in doing so. The first one is the tablet interferometer, which is very flexible for us. So we are able to customize and write gratings from 300 nanometers to 2.1 micron. And those can be customized in shape, so phase and amplitude. We, of course, also use the phase mask technique, which is a good technique to make repeatable FPGs that can also be customized, but there's an investment up front. You need to purchase the phase mask. So if we have the phase mask in stock, we can use that. But if we don't, it typically has an additional cost to do so. So one example that I said was relevant for the FPGs is this narrow line width filter that we made at 795 nanometers. So we provide minus 3 dB bandpass at less than 1 gigahertz. So you can filter less than 1 gigahertz line at 795 nanometers. And that's made, of course, in a TM fiber. Once we have that also, and because we can make narrow line width filters, we can also make narrow line width lasers. Another advantage that we have at iXblue is that we make the doped fibers. In this particular case, we used a helium doped fiber to make a narrow line width laser at 1908 nanometers. This one was used to generate 852 by mixing with 1540 nanometers. The advantage is that you can get narrow line width, so less than 10 kilohertz, up to 1908. And we provide that in a very short optical cavity, actually, because we write the grading directly onto the built fiber. So it's a very short cavity. It's something that you can use to build your own laser. We only provide the fiber that's built with the grading written into it, and then you can assemble it with a pump and generate your laser. And we get very good results, water-free, very narrow line width. So it could be a good solution for you if you're looking for customized wavelength. So we had a 2 micron. We also make them at 1550. So if you have any questions on that, I'll be happy to answer after the webinar is done. So now to conclude, I will yield to Hervé, who will give you a little summary of our product portfolio.
Yes, good morning, good evening, everyone. So I have the responsibility to conclude this, this presentation. So next slide, please, Yves.
Yep.
So I guess you have understood that our aim for the today presentation was to introduce where and how the lithium niobate modulator are used in the laser which are built for atom physics. I guess you have seen that you have identified that we have dedicated lithium niobate modulators for each of your lasers. We have seen that several lasers are built, multi-lane lasers, com-generation lasers, single laser, also narrow sub-nanosecond pulses lasers, and also laser with frequency looking based on PDH technique. For each of these lasers, we have one dedicated lithium niobate modulator, phase amplitude, or IQ modulator. We have introduced also our collaboration with the iXatom lab, where we have developed a very specific 780 nanometer laser source. Definitively, I guess you have also understood that we have the best lithium niobate modulator phase and amplitude for near-infrared window, and especially for the high optical input power capability. Also, I guess you have understood that we have a specific MXIQ modulator based on an IQ modulator design, which is necessary to generate a single sideband carrier suppression signal. Also, we have introduced a few of our mod boxes, which are turnkey optical transmitter, and which are definitively the ultimate modulation solution where the best optical performances are wanted. So in this picture, we gave the main and typical performances expected from this lithium niobate modulator. First, you have typically the optical spectrum we are able to cover. So from 760 to more than 2 microns. And below you have a star, which provides you the specificity and the several options we are able to provide. So if we begin from the right side, optical power and link capability, HOP option. This is very important to understand that in the near-infrared window, we are able to provide some modulators where the refractive index effect is limited. And this offers us the capability to provide some lithium niobate modulator with high power and link capability. We have also understood that for PDH technique, it is necessary to mitigate the low residual amplitude modulation. This is possible because we offer a DC coupled phase modulator. As well, it is very, very important also that all this specification, all this optical specification are stabilized over time. So insertion loss, polarization, extinction ratio, and extinction ratio. This is possible because we are using X-cut design, and also because we are using a unique proton exchange manufacturing process for the optical waveguide. Also, and of course, for all the lasers, it is important to provide low insertion loss modulator. And for sub-nanosecond optical pulses and for single photon laser source, we are able to provide high extinction ratio amplitude modulator. As well, for some cases, it is necessary to provide high polarization extinction ratio modulator. And this is also possible because we are using indeed proton exchange process. If we refer now to the electrical specification and the option we are able to offer, we have seen that in some cases, and it is the case for COM generation laser source, it is necessary to provide low VPI modulator. So we have a dedicated bandwidth modulator for that. Also, for very short, let's say fast rise and fall time optical pulses source, we are able to provide very wide bandwidth electro-optical modulator. As well, we have introduced a project, the Grace Follow-on project, and we are able to provide space-graded components. As well, again, because we are using X-cut design, our modulator has very low drift. And of course, for all the components, all the modulators we are supplying, we are capable to provide the matching components. I mean, the RF amplifier and the modulator bias controller, which will fix the bias point to the amplitude modulator. And then the final product for the lithium iodide modulator solution are the mod boxes. So the mod box are clearly the ultimate performances we can expect from our own product. For the laser pulse, we are capable to provide very short pulse from 30 picosecond to more than several hundred nanoseconds. This is a great performance, and this is due to our wet component. From these pulses, we can generate very square shapes pulses, but also controllable waveform pulses by the use of arbitrary waveform generators. You have been also introduced a mod box we have co-developed with iXatom lab, and this solution is providing 2 sidebands at 780 nanometer, 500 milliwatt. As well, you have been introduced also some very flexible solution for single sideband generation at 1560 nanometer, carrier suppression, residual carrier suppression, and full carrier suppression. So again, all this modulation solution, the mod box will be based, on your requirement. That means even if we have a dedicated product and standard product, iXblue is always capable to adjust, adapt, and optimize a dedicated solution based on specific requirement. Yves, maybe?
And then, and then finally, for to get your high optical signal purity, we went over some solutions to increase the polarization of your laser. And there we have solutions available that are standard for 780 nanometers, 840 nanometers, 1053, 1054, 1310, and 1550 nanometers. To customize if there's a need for it. We've shown our capability to provide now 9 with optical filters with a bandwidth as low as 1 gigahertz through that max, and the ability also to provide you with the tools to build your own now 9 with DSP sources at 2 micron or in the C-band. And that concludes the presentation, so that we are open to questions if anybody has some questions. But thank you again for attending, and we look forward to discussing with you.